Okay, so for the last lecture, I'm going to talk about a different approach to designing tests of quantumness. It's going to have its own advantages and inconvenience. The main advantage that we're going to be looking for is to have a test for which there is efficient verification. Okay, that was one of the drawbacks that I pointed out about random circuit sampling, is that verification was not efficient, and so that prevents you from using the test at larger circuit sizes. Verification becomes impossible. So in order to explain how we're going to achieve this, I'll again introduce a little bit of background in complexity theory, but hopefully it'll stay very simple. So complexity theory studies computational problems and tries to classify them according to the difficulty of solving these problems. So in general, to study a class of problems, we associate a language to it. This is not so important. So let me go over just three basic complexity classes. The first one everyone knows is P. So a problem is in P if I'll write it here, there's an algorithm. This algorithm should run in polynomial time in the length of its input. So it receives an input Z, which is an n-bit string. It runs in polynomial time in n, and then it outputs a decision, yes or no. So in general, for simplicity, we focus on decision problems. And the problem is in P if this algorithm makes the correct decision all the time. Okay, so for example, a primality testing is in P. So Z is a number, and you have to decide if the number is prime or not, and there's an algorithm that does that. Another example is graph connectivity. There's many examples. Unfortunately, yes, the answer has to be correct all the time. Yeah, so I am not writing, yes, the answer has to be correct. So unfortunately, not every problem that we care about lies in P. So there's many problems that we find interesting, but there's no efficient algorithm for solving them. An example is the three coloring problem. Here, the input is a graph, and you're trying to decide if it's possible to color the vertices, the nodes of the graph, using 3 different colors at most, such that for every edge, the colors of the endpoints should be different. So we don't know of an algorithm of doing that. You could try all possible colors, but there's 3 to the n, if n is the number of nodes, possible colorings, and so that's going to take you time, naively at least, 3 to the n, and that's not polynomial. So there's no algorithm that does that. So for problems that do not lie in P, we try to find other ways to characterize them, other distinguishing features. Tree coloring has the distinguishing feature that even though it's hard to decide the problem by itself, decide if the graph is colorable or not, it's actually easy to verify proofs that the graph is colorable. So that's a problem that lies in the class NP. And the class NP is the same, except you imagine that there's some entity here. So this is an all-powerful entity called the prover. And there's a statement that this prover can provide to you. I'll call it pi. This is called the proof, such that 2 things hold. So for inputs for which the answer should be yes, the graph is colorable, there should be a proof that makes you accept. Okay? The proof would be a valid coloring. You'd check it. This is very quick, and then you'd make the right decision. For inputs that are not in the language, then whatever proof comes to you, you should reject. Okay? So NP is the class of problems that are efficiently verifiable. And if you have in mind what we've been doing so far, this is kind of the kind of problems that we want to study. In this black box verification problem, this is the black box, and I'm giving it an input. The answer is not, I'm sorry, so, sorry, I said something wrong. Yeah, what I meant to say is that we're looking for problems such that okay, so I guess I was being loose. We're looking for problems that can be efficiently verified, but we're not actually looking for problems. We're looking at tests such that the verification can be efficient, but it's natural for these tests to look for problems that are in NP, where we'd be asking the device to provide the proof. And this proof is something that can be efficiently verified. And if we find a problem such that proofs for the problem can be found by a quantum computer, but cannot be found by a classical computer, then it's going to fit in that framework. So an example is factoring. Okay, factoring would be a problem such that the proof is just a factorization of the number. This proof can be found by a quantum computer, but as far as we know, no classical computer, and it can be efficiently verified. So factoring is a problem that's in NP. The reason it didn't really work for us is that finding the proof is quite hard on the quantum computer, and also the classical hardness is kind of ad hoc. I mean, you have to assume that the problem is hard classically. Okay. So there's one step that we can make and that I'll make for this.
For the example you gave for coloring, coloring a graph, would the proof be for a specific graph, like a specific
Yes.
color?
Yes. So you're right. This is the graph. The graph also goes here, and this entity has as much time as they want, so they'd compute the coloring, they'd give it to us, and we'd be able to check it very efficiently. And this system is going to work for any graph. For any graph, it's possible to do that. Unfortunately, I can do it again, not every problem that we care about lies in NP. A nice example is the graph non-coloring problem. Okay? So here you're given a graph, and you want to say yes when it's not colorable. How do you prove to someone that the graph is not colorable? You can tell them try, and you'll see it's not. That's not a good enough proof because I can say the same thing when in fact it is colorable, and this guy will make a mistake if they believe what I'm saying. So as far as we know, the graph non-colorability problem is not in NP, but it's in a slightly bigger class, which is called IP. I stands for interaction, and the difference is that we're allowed to ask questions. That's one difference, sorry, allowed to ask questions, and the other is that this algorithm is allowed to be randomized. And because it's randomized now, it has to make the correct decision with very high probability, let's say 99.9%, but there can be a probability that it makes the wrong decision. So for any input with 99%, it needs to make the right decision. So this is not at all an easy fact to see, so I won't explain it, but the graph non-coloring problem can in fact be verified by interacting with a no-powerful prover. At first, maybe they'll tell us, okay, it's not colorable, but then you'll say, okay, like explain, and there's more complicated questions coming, and then you'll be able to make the right decision. So the first important point is that the ability to interact with a machine, with this all-powerful machine, increases the class of languages or problems that you're able to verify. So this should be useful for us. Maybe if we can interact with this black box, now we have a broader class of problems that we can verify, and maybe some of these problems are easy for quantum computers, and this would be great for us, okay? So that's where I'm going. In fact, this class has been studied extensively in complexity theory, and it's characterized. I'll just write the characterization here. Any problem that can be solved in polynomial space, but maybe exponential time, okay? So it could take exponential time to solve the problem, but as long as you can solve it in bounded space, you can also verify it in bounded space and bounded time in this framework. Okay, now one more equation is that BQP is the class of problems that we care about. This is the class of problems that can be solved by a quantum computer, like a perfect fault-tolerant quantum computer, okay? This class of problems actually is in p-space. This is because any computation, quantum computation that can be realized in polynomial space and time, you can simulate using polynomial time and exponential space just by doing very efficient like matrix multiplication kind of operations. Okay, so
Time in the exponential space, you mean the other side? Time in the
no, both are possible. Okay. But here I care about the one where it's polynomial space and polynomial space and exponential time. Okay, so if you trace the equations, what this means is that for any problem that the quantum computer can solve, including, of course, noisy computers, even the fault-tolerant ones, this problem has an interactive proof of that form, meaning that I can input here the name of the problem, what the task is, and this problem can be verified in polynomial time, provided that someone is able to resolve that interaction for me. So this seems to suggest that, in fact, any problems that the quantum computer could solve can be verified efficiently, including random circuit sampling and these kinds of things. That's true, but there's a caveat, as always. The caveat is that this sequence of equalities doesn't say that the proof can be generated also by the quantum computer. Okay? So the problem can be solved by the quantum computer, but if we try to verify it in polynomial time, this interaction might require much more power of this in order to generate the valid proof and valid answers, much more problem than just solving the problem. We're asking more complicated questions here, and the quantum computer in general will not be able to answer these questions. Okay? So now but it opens some directions for research. What we're going to try to do is try to find some problems that are in BQP. We want them to be able to solve by a quantum computer, and that are efficiently verified. So they're verifiable. The problem should be in BQP, and there should be a setup like this, where this is the verification procedure, and whatever proof I'm asking of the device, this can also be generated by a quantum computer. Okay, so this was just a little bit of background, and now I want to get to the meat of it. So still, overall, we're trying to find a quantum advantage for something. And this was pointed out in my first lecture, which is that the first examples of quantum advantage that people study in quantum computation are for oracle problems. There's the Dirtiosa problem, there's Simon's problem. So what we're going to do, the basis for what we're going to do is Simon's problem. So I need to remind you a little bit of what Simon's problem is. Hopefully many of you have seen this, and so it'll be quick. So Simon's problem is based on what's called a 2-to-1 function. So it's a function that maps n-bit strings to n-bit strings. And it has the structure that it's 2-to-1. What does 2-to-1 mean? It means that if I plot here the inputs x, and here I plot the outputs of the function y equals f of x, they come in pairs like this. So there's always, for every y, there's either 0 or 2 x's that map to it. Never 1 or 3 or anything like that. So maybe like this. Okay, that's an example of a 2-to-1 function. And so a triple of 2 inputs x0, x1, and y that satisfy this, we call that a claw often, because it kind of looks like a claw or something. So, okay, so this is a claw. Okay, so what's something fun that you can do using a quantum computer and a 2-to-1 function? So let me tell you. You do kind of like the only things, this is Simon's algorithm, you do the only things that come to mind. So you're going to first create a uniform superposition over all possible inputs to the function, x, and you're going to evaluate the function in superposition in some ancilla register. So as long as this function is given, sorry, f of x. Sorry, bad board usage here. As long as this function is given by a circuit or a formula or something, in principle, you can do that. And now let's measure the output register. So measure the second register. I'll get some y in the range, and this register will collapse to all the x's that are consistent with the y that I obtained. By definition, there's exactly 2, so I'll get a superposition of x0 plus x1. Okay? So what can I do at this point? I could measure, and I would obtain x0 and y, for example. I didn't need a quantum algorithm to do that because I could have chosen x0 and compute the function and get y. Okay? If I could get both x0 and x1, this would be interesting because it's not obvious how to do that in a classical computer. But I can't do it either here. If I measure, it collapses. What I can do is I can measure in the Fourier basis, in the Hadamard basis. So measure in Hadamard basis. And what's going to happen, I'll skip the calculation here, but if you do the Fourier transform, you'll get a big superposition with many phases. But because this has amplitudes on only 2 states, there's going to be some cancellations. And what you'll get is that you'll get some string d, which is an n-bit string. And it has to be such that the inner product between d and the parity of these two, x0 and x1, is 0. Okay? You do the calculation, and this is what you get. Okay, so what Simon observed is that this can be very useful if we know one more thing about the function. If it's what I call like a Simon's function. What's a Simon's function? It's a 2-to-1 function, and whenever there's a claw, these claws always have a very special structure, which is that the preimages are related by some s, and s is always the same. Okay, so if I take the difference, the parity between these two, I get s. These two, I get s. These two, I get s. Always the same. Oops. So if we assume that that's the case, then this is s. In particular, it doesn't depend anymore on the y that we obtained from the measurement, because the parity is just always s. So every time I run this, I get an equation in s. So if I run it n times, maybe a bit more, because s has n bits, I'll get many equations. These equations are obtained at random. Soon enough, they'll be linearly independent. I'll be able to solve and recover s. Okay, so run n times, recover s. Okay? So this is what Simon's algorithm does. It takes something known as a Simon's function. It's a function that has that structure. And by running this simple quantum algorithm n times, it's able to recover n or a bit more than n equations in s, and then do Gaussian elimination to find what s is. Now, why is this a quantum advantage? Because if you know nothing else about the function and you ask yourself, okay, how do I figure out S classically? I mean, as soon as I get a claw, I got it, right? How do I find a claw? I take some x's and I evaluate them. I'm going to take this x and find this y. Then maybe I'll take this x and find another y, and this x and find another y. And once I've taken enough x's that I found two that map to the same y, I'm done. The problem is that there's exponentially many x's and exponentially many y's. And so in general, even using the birthday paradox, it's going to take me time 2 to the n over 2 in order to find such a claw. Okay? So this is why Simon's algorithm gives an advantage. There's a quantum algorithm that has n steps, but the best classical algorithm will take 2 to the n over 2 steps. So it's an exponential step version. Okay, can we use this? There's one problem with using this is that we can't come up with any concrete function f that satisfies this condition and such that there's no classical algorithm that uses this concrete structure to break it. It's a little bit like my worst case to average case difficulty earlier, but it's subtly different. It's just any kind of function that I can write down. No, these functions, they could be x plus 1 or x times 2 or x squared or, of course, so many more, much more complicated things. But they need to have this structure. And whenever they have this structure, I can actually use that to break it. So Simon's algorithm only works if this function that has no other structure than that can be used. But we don't know of a function that has no other structure than that. Okay, so we can't use Simon's algorithm directly. What we can construct, and this is what I'll use for the test. So now I'll describe something a little bit stronger, a little bit different from a Simon's function, which is something I can construct. And then after that, I'll describe the test based on it. I'm going to claim that functions with the structure that's on the slide can be constructed. So what are these kinds of functions? But they're not Simon's functions, okay? Simon's functions have too much structure. This is too much to ask. I just can't create functions that satisfy this and are not easy. So instead, I'm going to do the next best thing that I can come up with, which is what's written on the slide there. So we're going to construct a function, which is, it's still 2 to 1. I'll have some arguments. So these are cryptographic arguments. For y, for that function, it's hard to come up with claws, okay? So coming up with x0, x1, and y that form a claw, this is hard. What does it mean hard? Well, this is an explicit function. I could give you the formula for it. And if some classical or even quantum algorithm is able to find a claw, remember the Simon's algorithm, it doesn't find a claw, right? It finds this s and just one x0 or x1, but not both of them. So if a classical or quantum algorithm was able to find a claw, then they'd be able to solve some problem, that some cryptographic problem that no classical or quantum algorithm can solve. So it's like factoring, but it's harder because even no quantum algorithm can solve it. Okay, so no one can find claws for the functions that I'm going to use, except if you have a trapdoor. So the trapdoor is some secret information that's associated with the function. For example, think of prime factorization of some number, something like this. Some secret information associated with the function, that if you have the secret information, then you can find the clause. Okay? But no one without the secret information can't do it. And then there's a special property, which is kind of like next best thing compared to the Simon's promise, which is that it's hard to do the following. So it's hard to find x0, x0, y, d, such that, and there's going to be two conditions. The first one is that the function maps x0 to y, and the second is that the equation d and, the equation d is an equation in the parity, a valid equation like this, okay, and d is not the zero string. This is a strengthening of this condition, okay? If you could find a claw, then you would have x0, you would have y, and you would have x0 and x1. So you could compute their parity, and it doesn't matter if it's always some s or if it's not always some s. If you can compute this, of course you can find equations in it. You just, this would be easy. So this is a stronger condition than that. And there are some very simple functions that we can construct that satisfy all these conditions. But I don't have time to tell you what the function is, but it's based on linear algebra. They're very simple functions. For those of you who know cryptography, these functions are constructed based on the learning of errors problem, which is a standard assumption for post-quantum cryptography. What I want to do, though, is that ask you to believe that I can construct explicitly functions like this and design a test of quantumness based on that, okay? These functions do not satisfy Simon's promise, so I can't run Simon's algorithm, but I can do something else with them. I just want to emphasize that when I say hard, this applies to classical and quantum, okay? So my test is not going to be like, okay, I'm just assuming that this is hard for classical and easy for quantum, so why doesn't the quantum do that, and then we'll be done, okay? That would be trivial. I want to do something a bit more subtle. So this is just hard for everyone, yeah?
Is there anything about the number of sliding pairs?
Well, implicitly, yes. Did I write? No, the function is 2 to 1. So, you know, it's just the number of inputs divided by 2. Okay, so the test is as follows. So it's going to differ from the test that we considered before. When I introduced the setup in the first lecture, I said, this is the device. I have to select inputs. It produces outputs, and I need to check these outputs, and then I'm done, okay? Now I'm going to require a slightly more complicated setup where you can do this twice. So you can send something to the device, it generates some output, you read this, and then you go back and then you perform a second round where you provide some new inputs and then it provides some new outputs. And you do that sequentially. So I wrote it using the language of interactive proofs on the slide, but it's similar. So think of V as the entity that's running the test, the verification procedure, and P stands for prover, but it's what the quantum device is supposed to do. So I'll run the test for you, assuming ideal behavior of the quantum device. Okay, this is what my test is asking you to do. Of course, I don't know what you do in practice, but we'll argue about that after. Okay, so at first I tell you what the function is. Okay, so this function is specified by an explicit formula. I can just tell you what it is. And I ask you to run the first few steps of Simon's algorithm. So you create a superposition, evaluate the function in superposition, measure an image, and if you did everything correctly, you'll get the superposition over 2 pre-images. And I ask you to report the image that you obtained. Okay, so this is at this step here, we get some y, and I just store that. Now at the second step, I'm going to flip a random coin. I call this a challenge, but it's just 0 or 1. I'm asking you to do one of 2 possible things. So if the challenge is 0, I'm asking you measure in the standard basis. And remember, these are just instructions, right? What they do, I don't know. I'm just telling them, please measure in the standard basis. If they do it, then they should obtain some x that's a pre-image of the y that I obtained before. And I'm going to check this, okay? So when I execute the test, here will come out some x, and I'll evaluate f on x and check that f of x is equal to y. The other challenge corresponds to please measure in the Hadamard basis. Okay, so if they measured in the Hadamard basis, what's going to happen, we did the calculation before, you're going to get the string d, whose inner product with the 2 pre-images is equal to 0, and I'm going to check that. Okay. So that's the test. It's a well-defined test in my sense because all the actions that the verification procedure does are well specified. It chooses a function, it sends it, I haven't told you what the distribution on functions is, but there is such a distribution. It sends it, it expects a y, it puts it aside, it generates a random challenge, it waits a bit, then it gets an x or a d and it performs the checks that are there. If the checks pass, it accepts. If they don't pass, it rejects. Maybe it runs the test not so many times, not millions of times, maybe 100 times. And if the number of checks that passed is bigger than, let's say, 90%, then the device is accepted. Okay? Okay, so now we have to check a completeness, concrete or not, and soundness, etc. So we have to talk about these things. So how about completeness? So if the quantum device is not noisy at all, then it's easy for it to succeed all the time, 100%, just by describing the steps that were on the board and that I erased. You prepare these superpositions, you do the correct measurements, everything is going to check. If the device is noisy, well, it depends. I don't know. It depends on the amount of noise.
So what does succeed mean?
There's an accept condition at the bottom left. It means that it's always going to be satisfied.
But to get D, I need equation or I need many?
No, D is not the same as S. D is just something that satisfies this equation. So just one.
So I get one equation, but many unknowns. D is a law effect?
Yes. That's okay. This is what the test asks. It asks for just one equation. So I just checked that equation is valid. It doesn't allow me to recover x0 and x1. It shouldn't. Now it's erased, but one of the assumptions was that for these functions, no one can recover a triple x0, x1, y. No one. So even not the quantum part, not the classical part, no one can do it. So I'm not asking anyone to do it. What the quantum part can do is just find either one equation or one preimage. Okay, so now let's talk about soundness. What's the classical hardness? So, okay, here I have space for a proof. Okay, so I'm going to try to make that argument. So now the argument is that suppose that there's a classical device that's used in order to execute the protocol. So it doesn't create superpositions or anything. It does whatever it wants. But it still has to return a y and an x when I ask an x and a d when I ask a d. And suppose that it succeeds with probability, let's say, noticeably larger than 3/4. Okay, let's say 0.8 or let's say 0.9 because that was my threshold. I want to claim that that's impossible. That contradicts an assumption that I made earlier. So why is that the case? Well, the key observation is that if a classical device succeeds with probability strictly bigger than 3/4, then let's do a more fine-grained analysis and compute the probability that it succeeds when the challenge is 0 and the probability that it succeeds when the challenge is 1. Okay, so let's call these P0 and P1. The overall success probability is half P0 plus P1, okay, for the classical or the quantum device, because I choose the challenge to be 0 or 1 with probability half. If it succeeds with probability bigger than 3/4, then this should be bigger than 3/4, okay? These are numbers between 0 and 1, so this implies that P0 is strictly, okay, let's just give ourselves a little bit of wiggle room here. P0 should be bigger, okay, I'll put, I don't know, 0.9. This way I'll get P0 bigger than 0.8 and P1 bigger than 0.8. In fact, it's probably, yeah. Okay, both of these conditions need to be satisfied, otherwise the average will never be bigger than 0.9, even if one of them is 0.8 and the other is 1. This is how you get to 0.9. Okay, so this means that this device is able to answer the challenge 0 with probability at least 0.8 and the challenge 1 with probability at least 0.8. Yeah, question? Because this was my threshold for the test. So the test accepts if I do a certain number of runs and 0.9 of them pass. The quantum device can pass 100%, so it's more than 90%. And now I'm trying to argue that if a classical device succeeds in 90%, let's do it like this, then that's impossible. I want to argue that that's impossible. So it was kind of arbitrary. I could have chosen any value between 3/4 and 1, but this one is just convenient. Okay, so what does it mean that you can succeed for the 80% and 80%? This is where we're going to use classicality in an interesting way. If you're a classical computer and you're sitting there, and I send you challenge 0, please give me x. Okay, they do it and they give a correct x for the 80%. And then I challenge them, or I could have told them challenge 1, give me d, and they give me d for the 80%. Actually, I can ask them both of it, right? I can ask them, please give me x equals, please answer challenge 0, then I get the answer. And then I would say, okay, reset your memory to whatever it was, and then answer the challenge equals to 1. Okay? They might not comply, but in principle, according to the laws of physics, classical behavior is rewindable. I can repeat it. If there's two possible behavior that leads to this x and this d, I can run them simultaneously. So what this means is that, okay, implies the classical device can return both x and d that are correct with probability, I mean, without doing anything fine-grained, let's just take 0.8 squared. So it's anyway some positive probability, okay, some significant probability, not bigger than 0.5, it doesn't matter. They can return both x and d. But that's the thing that I assumed hard, right? I wrote it here. It's hard to find x0, y, d such that f of x0 equals y and d is that. So it's hard to answer both challenges simultaneously. If a classical device succeeds in the protocol and it can answer the one challenge or the other, each of them with significant probability, then it can also answer both. I could just, in principle, ask both challenges. So it means I would be able to satisfy that, and I can leverage this. I didn't show you this part, but I can leverage this in order to design an algorithm for some problem that doesn't have an algorithm. So why didn't this apply to the quantum procedure? Well, the quantum procedure is written here what it does, right? On challenge 0, it measures in the standard basis, and that works. On challenge 1, it measures in the Hadamard basis, and that works. But I can't ask it to measure in both bases. That doesn't make sense, right? Once you've made a measurement, you can't go back. You've destroyed the state. If you measure in the Hadamard basis, you'll get something completely random. You can do it twice, but if you do it twice, you have to restart all the way from the start, okay, to generating the superposition. But this superposition will in general be obtained with a different y. And so in that case, what you'll obtain is that you'll obtain x0, y1, d, y2, such that this is y1, but this is for the pre-images of y2. And then that I can do using a quantum computer, but it's actually not helpful. Yeah.
just not shown that there are certain tasks where not performed by the computer. Oh, you are claiming that this problem cannot be solved by now.
No, exactly. Yes, it's the second part. So what we're trying to do is that this is a test, and this test can be satisfied by a quantum device pretty easily. But if a classical device succeeded in the test with probability bigger than 90%, then I could use that classical device in order to break a problem that cannot be broken. And that's my assumption is that this problem cannot be broken.
So it is more than proper that the probability is the classical device, classical device cannot succeed in the probability more than I don't know, 30, 50%.
Oh, it's like anything that's non-negligible. You mean for this thing?
Yeah.
Yeah, any inverse polynomial is fine. So, yeah. No, I didn't need 0.9. I only needed 3/4. Because if you succeed with probability, here's one way to succeed with probability half in that test. That's easy. I choose x at random and I compute f of x equals y. Okay, I just do that. At the first part, when you ask me for some y, I return y. In the second part, if the challenge is 0, I tell you x, and you'll accept f of x is equal to y. This is how I chose it. If the challenge is 1, then I'm kind of lost, so I answer something random, and the chance that that random thing succeeds is a half. So what's my overall success probability? If the challenge is 0, I succeed with probability 1. If the challenge is 1, I succeed with probability half. So overall, 3/4. So 3/4 is easy, and the argument is that anything noticeably bigger than 3/4, that's hard. Okay, so we did the proof. These are some references, and I guess I mean I don't want to go over the references. Maybe let me go directly to the next table. So I want to discuss a little. So that's the end of the description of the test, and now I want to discuss it a little bit by going over some advantages and inconvenience of what we did, just to recap a little bit. So let's start with the advantages. The main advantage of this approach is that you can, in principle, run it for all levels of hardness. So this function f that I choose, I can tune the size of the function, I can tune the size of the pre-images, the images, everything. It's gonna make it harder for the classical device to succeed. It's gonna also make it experimentally harder for the quantum device, but the verification will always remain efficient. What makes this verification efficient is this idea of trapdoor that I introduced, and then I forgot to talk about it. So in order to verify that the equation is correct, you need to know what x0 and x1 are. And I said x0 and x1, finding them is hard, unless you have the trapdoor. So the verifier is using this trapdoor in order to enable efficient verification. So trapdoors are something that's an idea that's used a lot in cryptography, where you have a problem that's hard, unless you know some specific information about that problem. And moreover, because these things are meant to be used for cryptographic purposes, it is known how to generate an instance of the problem that's hard together with the secret that allows you to break it. And here, this is what's going on. We're generating a function f that's hard, sending that to the prover, and keeping some secret information to ourselves that is going to be used at the step where we verify, the tests. That's one advantage, so efficient verification. That's the main thing that we wanted to achieve. Another one is that there's kind of like a large gap in a way, right? Before we were talking about epsilons, and here the gap is between 3/4 and 1. Presumably, when I do the experiment, you know, maybe I'll see maybe 0.9 for the quantum computer, and this is still like very much bigger than 3/4. So there's a large gap. It sounds nice, but unfortunately, things are not so nice. You know, if I try to really explicitly write down the quantum circuit that this device is supposed to execute, then that's actually too hard for current state-of-the-art experiments for two reasons. One is that what's the number of qubits required in order to do that? I wasn't very specific here. There was just some n, that's the number of inputs. And you saw the quantum circuit, it looks pretty easy. You do a superposition over all x, evaluate the function, and then after that it's just measurements. That's it. So it doesn't look that complicated, but evaluating the function f, it kind of depends. This function f is not so complicated, it's linear algebra. Potentially it can be implemented in a small depth, something like log depth. Unfortunately, what's the n that you require? You require an n that's sufficiently large for the cryptographic problem that underlies this whole setup to be hard. For the case of random circuit sampling, you could have some pretty sharp arguments that say that any n such that 2 to the n is too much time is hard. So 53, 2 to the 53 is like too much time, and then that was good. Crypto, there's always a little bit of overhead because you use problems that are more structured. And so to the best that people can say, the number of qubits required in order to perform a convincing test of quantum advantage, demonstration of quantum advantage using this approach would be something like 200 qubits, which we don't have because we still need to be able to prepare these uniform superpositions, etc. And if the noise rate per qubit is a constant, it's just not going to work out, right? You won't see anything above a 3/4. It'll be like in the Google experiment. You'll see 0.002 or something like this. And if succeeding with already 0.002, unfortunately, in my test, it's easy. For Google, we might have hoped it was hard, but here it's easy. So this is not a very near-term proposal. It's a little bit of a longer-term proposal. What makes it maybe a little bit worthwhile, and that part I didn't have time to discuss, is that there's many potential applications. One that maybe I can highlight is generating randomness. So you can, in fact, argue, just I can do this without writing anything, that this is also a protocol for generating certified randomness. What do I mean by this exactly? Suppose that we run this test many times sequentially, and each time we record just one piece of information, okay, whether it passed or not, and in the cases where the challenge was 0 and I got a preimage X, I record whether this was the X0 preimage or the X1 preimage. Okay, suppose that these clauses are always labeled. So for every Y, there's 2 preimages. The verification procedure can compute them using the trapdoor, and also there's one that's labeled, the first one, and one that's labeled the second one. So I do this test many times, and I just record did I get from the prover the first preimage or the second preimage. Okay. So 2 observations about that. First one is that if the quantum device implements the protocol, whether it gets the first preimage or the second is a uniformly random bit, okay, that it couldn't have decided on, because it just measured this superposition in the standard basis and it got 0 or 1 of probably half. That's the laws of quantum mechanics. That's the first claim. Second claim is that, in fact, anyone who succeeds in the protocol cannot possibly have chosen which preimage they will return to me ahead of time. Okay, why? That's a little bit more subtle. You need to know one fact about quantum measurements, which is that if you make a quantum measurement such that the outcome of the measurement is predetermined, then in fact it doesn't alter the state. Okay, that's called gentle measurement lemma sometimes. If the state is such that the outcome is determined, that state was an eigenstate, and so making the measurement doesn't disturb it. So suppose that you try to devise even a quantum algorithm that succeeds in the protocol, but when it returns a preimage, this is always the 0 preimage. So it means that whatever measurements it makes on challenge 0, the outcome was predetermined. It's the 0 preimage, x0, which is uniquely defined from y. If that's the case, by what I just said, this measurement can be undone. And so in fact, any such kind of quantum device is able to answer both challenges. I can challenge it for challenge 0, it'll return x0, and because this measurement had a deterministic outcome, it didn't alter the state, so in fact I can run the measurement for c equals 1 and also get d, and that's impossible. So maybe this went a little bit too fast, but it's not hard to make the case that this protocol must generate randomness. There's no way to succeed, even if you're quantum, by determining in a way that the answers are determined ahead of time.
You have also to create randomness.
That's true. So then you have to create randomness because you have to select F, and F is chosen from some random distribution, like the random circuits, but it's something else, and I didn't describe that. And that requires a lot of randomness. So if you do the protocol many times, you can have some cost savings. You can reuse F, or maybe generate different Fs at each step, but using very little randomness. That's done in a paper by Bakarski and me and some other people. So, but you need to work a little bit harder, but you can do it. Still, even if you got less randomness out than randomness in, I claim that that's still interesting. Why? Because the randomness that you get out, you can really argue that this must have been generated on the fly. The randomness that you put in, you don't really know. It's your PRG, it's whatever. It could come from a public source. This is not something that's so trusted so much. Here, what you get out of the protocol, I mean, anyone who saw the transcript knows. But other than that, P could not have decided ahead of time. Someone who doesn't see the transcript cannot know what the randomness is, even if they knew your randomness for generating F. So okay, I think that's it. And one of the inconvenience maybe is this interaction, right? I kind of like cheated. I changed the model. Now I allow interaction. Is this a problem or not? I mean, I thought this would be fine, and then we did an experiment. So there actually has been an experiment on this proposal, but it's a very small size experiment. It uses ion traps and it uses 13 ions. So it can be classically simulated, okay? So it's not a test of quantum advantage. It's just a proof of principle. And this was done by Monroe and people at UMD. And I learned that, in fact, making intermediate measurements, right? Here, if you want to execute the protocol, you have to create this superposition. And this superposition was obtained by making a measurement on the Y that's not written on the slide, and keep the pair there coherent, and then later make a measurement, standard or Hadamard. That's actually hard. Like most experimental platforms, you can perform some evolution and then you measure, but when you measure, you just measure everything. And for the ion traps, they had to work a little bit in order to make that possible, but in the end, they managed. So my point is just that it's potentially an additional experimental hurdle that the text is interactive, but it's not unsolvable. Okay, so 2 minutes to summarize. Yeah, okay. Okay, so this is the summary for the entirety of the lectures, and the summary. This is why also I thought it's nice to talk about this, even though the upshot is a little bit negative. I mean, the random circuit sampling, we don't have good enough evidence, and this proposal we have good evidence, but we can't really execute it right now because it opens. It means that there's some open problems to solve, and so my challenge to the audience for the future is: are you able to devise a family of tests in the framework that I presented that satisfy the 3 conditions that are written here? First of all, we'd really like these tests to be implemented on actual devices. Not necessarily now, but let's say in 5 years or maybe 10 years, before you have fault tolerance. Once you have fault tolerance, you can do many more things, and this will be great, and this is what we should be working on. But in the meantime, we can try to think about this. So meaning like hundreds of qubits, maybe 1,000 qubit, and the 2 qubit gate fidelity is 99.9 or 99.99 if you want. That would be fine, but not something ridiculous like 10 to the minus 9. Okay, so we want this to be kind of like in principle executable. There should be efficient classical verification at all sizes. This is because I don't expect that I can really do the experiment for 70 qubits and have convincing evidence. I want to be able to do it for 70 qubits, 100, 200, 500, 1,000. So I can see the scaling, and really I get into regimes where my classical hardness is solid. But in order to do that, I need to be able to efficiently verify instances that are large, over thousands of qubits. And finally, I want this to be theoretically sound. So I want the best evidence that we can find for hardness of classically succeeding in the task. And in the lectures, I presented 2 approaches. The one I just talked about now is based on making post-quantum cryptographic assumptions, and these I consider them safe because there's an entire community of cryptographers working on, 30 seconds, on trying to break these assumptions, and so far they haven't succeeded. Even safer are complexity theoretic assumptions, such as P different from NP. And very important is that I would like the hardness argument to apply to the noisy task. It should apply not only to the ideal task, like it did for random circuit sampling, it should apply to the experiment. So whatever the experiment is, I have to model the noise for it, I have to extrapolate probably a little bit, and then have some arguments that say that succeeding in the task with that level of noise, that's classically hard. Okay, that's it.
F is not an oracle, right?
Yeah.
So, for example, in the experiment run by F,
Yeah.
which you program,
Yeah.
and how do you know that F is, the knowledge of that F can't be used to solve?
Yeah. So that's the advantage of relying on cryptographic assumptions, because this crypto is used, you have the same problem when you use a crypto system. So this F, the same family of Fs, is used to instantiate secure channels. And when you do that, you also have to select an F at random, and you have to publicize it. And you want to be sure that that particular F that I chose cannot be broken, because it's the one that's securing my email. And so in cryptography, people have the same kind of average case to worst case reduction that we had before. They exist for these kinds of problems that I'm describing. In fact, with much better parameters, concrete parameters than what we had before.